Our next speaker, our keynote speaker, is Brother Guy Consolmagno of the Society of Jesus. He is the curator of media rights at the Vatican Observatory. And when I thought about being the first, moderating this for the first time, I thought, I wonder if I should get someone else to introduce Brother Guy. Asked some club members, and they said Francis. So I emailed, made a couple of phone calls, but Francis said he was still a little tired from his trip to Rio, and that he normally spoke to crowds of more 3 million than 1,000 or 1,200 people. Then I found out they meant Francis O'Reilly, one of our club members. Without further ado, I'd like to introduce Brother Guy Consolmagno, who will speak on Comet Tales, our changing view of these cosmic vagabonds.
Thanks a whole lot for having me here. I've got this gizmo, which when it works, controls from my cell phone. The first time I tried using this in the middle of my talk, the phone rang. But if it works this time, it'll be great, and if it doesn't, of course, it worked great half an hour ago. It doesn't work now. Oh, here we go. Here we go. Yes. Right. I'm a planetary scientist. I'm the guy who half wrote Turn Left at Orion. And while there's still enough light, I'd like to embarrass my co-author, Dan, by having him stand up. So if you need autographs from him, where are you, Dan? Right. There he is. He deigned to be my chauffeur this weekend as well, which is great. We've known each other since the days when I was a postdoc at MIT and he was a graduate student. And he even asked me to be his son's godfather. I think he wanted an Italian godfather for his son. I am a planetary scientist. I have 2 different research programs. One of them involves meteorites in a laboratory in one of the largest meteorite collections in the world, located in the Pope's summer home in Castel Gandolfo. And just to show you how much the Pope supports our work, he sent this chemist from Argentina into my lab, who brought his own white lab coat. It's very handy to have. He's looking actually at a piece of a meteorite called Epinal, which is from Argentina. People sometimes wonder why the Vatican supports an astronomical observatory, and I was going to give you a long spiel, but then I realized all you have to do is look at your own clubhouse, and you've got the answer written right on the walls there. Our own observatory dates from, we say, the reform of the calendar in 1582. But in fact, we've had astronomers on and off since that time. The modern incarnation dates from 1891. Pope Leo XIII at that point wanted to show the world that the church does support astronomy. It turns out most astronomers know that. It's the people in the church we have to keep reminding that the church supports astronomy. One of the wonderful coincidences about Pope Leo XIII, every pope has a coat of arms. His coat of arms has a comet. It was part of the family coat of arms. Comets have always been fascinating, wonderful, frightening, bizarre, because after all, they're unpredictable. Unlike anything else in the sky that can be used as a source of timekeeping, comets come at their own time, and it would be really hard to predict when they were coming. They come in very strange orbits, where everything else you could imagine was in a pretty much circular orbit around the Earth. It was really hard to understand the paths that comets took. And of course, they've got these weird tails. My own history of comets goes back a couple of comets I saw in my younger days. The first was in December of 73, I believe it was, Comet Kohoutek. No, you can't see it there. In 73, I was going to MIT and coming home to Michigan on the winter vacations. During Christmas vacation, I knew that Comet Kohoutek, if I've got it 73 wrong and it was really 72 or 74, I'm sure somebody here will shout out. 73, I got it right, good. I was told that you could see it rising just before sunrise. Out our front window, we could see this view. And I thought I'd just set up my telescope, about 7:30. It's still dark in Michigan at Christmas time. and I'm waiting for the comet to appear. I'd really never seen a comet before. I somehow missed Comet Bennett, Kiyosaki. I'm waiting for the comet, and it's getting brighter, and it's getting brighter, and it's getting brighter, and it's certainly coming to dawn, and I've given up. The only cool thing I saw was a crescent moon rising. But aside from that, I couldn't see the comet. And then I saw the sun rise and realized the crescent was in the wrong direction. It was the comet. I say that to remind you of how small comets normally are and how curved their tails can be when they're close to the sun. But that was my experience. Like a lot of people, Kohoutek, I'd been taken in by the publications and publicity that Kohoutek had. The idea it was going to be the comet of the century. It was going to be spectacular. Everyone's going to be amazed by it. And it really wasn't all that spectacular, as it turned out. It was a comet that had been seen early on because it was very distant, and they were just beginning to have telescopes that could pick these things up out beyond the orbit of Jupiter. And people had miscalculated how bright it would be. Fast forward a couple of years, I'm at the University of Arizona getting my degree in planetary sciences, and my roommate says, "Oh, there's a comet, you can see it." Yeah, or I've seen comets, they look like the crescent moon. "Oh, you get up at 4 in the morning." I'm not going to get up at 4. Well, I'm living in Tucson. Skies are dark. 4 in the morning, nature had me getting up anyway. So I figured, okay, I'll pull on my blue jeans and step outside. I walk around the building and looked to the east and saw Comet West. To give you a little bit of the scale, do you see the bright star in the upper right? That's Altair. And you can see in the midst of the comet there is Delphinus. This is covering a huge swath of the sky. And it looked like that to the naked eye. That is not any kind of time exposure. It was like standing in a planetarium and looking at a photograph of a comet splashed on the dome. It was the scariest thing I'd ever seen in my life. Because it was big and bright and shouldn't be there. So I could imagine, you can imagine, what it was like in ancient times when the stars were looked at as the one thing that, at least in life, was predictable, and to have something like that very unpredictable visit. What were these things? What were comets? What are the tails? Why do they have tails? What do these tails mean? How come the tails are always pointing away from the sun? They're clever enough to see that. Why do they have such funny shapes? For that matter, really, what are comets? Are they close to us? Are they far away from us? Are they things in the atmosphere? Are they things out beyond the moon? Because the translunarian sphere was considered the boundary between terrestrial things that act in a weird way and celestial things that act in a marvelously orderly way. What are comets made of? And where do they come from? This classic illustration, according to Pliny, of comet tails is marvelously hilarious to us now. I love the one that looks like a sword. But of course, it reminds us that when we're looking at things we don't understand, we always try to understand them in terms of things we do understand. And we see what we expect to see. In this crowd, I don't think I have to give you much of a lesson about what comets are. You all know them. You've probably seen more than I have. This is my what a comet is for anybody who's new to astronomy. Comets follow a path that mark as they go around the sun. The light and other radiation from the sun is coming up from the bottom right, and comets have a lump of something that's following that path, and they have often two tails, a dust tail and a gas tail. The dust and the gas are both being pushed away from the sun by the force of sunlight and by what's called the solar wind, a plasma that expands out away from the sun, carrying with it the sun's magnetic field. Things that are very light, like ions that can be carried away by the sun's magnetic field, are directed directly away from the sun. Things that move more slowly, like bits of dust about as fine as flour, will move slightly behind times as the comet itself follows this path around the sun. You see dust tail up at the bottom, up at the top, and dust trail along the path. And we'll talk a little bit more about what that trail is. So that's what we know today comets are. But it was a long path to get there to understand what comets were. One of the key advances, of course, was the telescope. And in 1618, after about a 40-year period when no visible naked-eye comets were seen, finally, this is only 9 years after Galileo had come up with the telescope, 3 comets were seen in the sky. So, of course, where was Galileo with his telescope? He was sick in bed. The first person to actually look at comets was a Jesuit priest named Orazio Grassi. And after observing these comets, he wrote a little booklet about it. And of course, being a Jesuit means that you're part of this international chain, international conspiracy. We're all completely, lots of schools, we do write letters to each other. He organized with a couple of Jesuits up in Germany to observe the comet and the position of the comet night to night. With this, he worked out the parallax of the comet and showed that comets are located out beyond the moon. Basically, one of the great things about working at the Vatican Observatory is that across the hall from my office is our library, and the Vatican libraries gave to the observatory all of their modern books on astronomy. By modern, they mean printed with a printing press. So I was able to go in and photograph a few of these marvelous books. This was the calculations that Grassi explains how he observed the comets and how the comet and the same night at the same time appeared next to exactly the same star, whether you were observing it from Italy or from Germany. Therefore, you could say that the comet had no visible parallax, had to actually be out among the stars themselves. And this was a really exciting discovery. And he was the first guy to observe a comet through a telescope. This did not sit well with Mr. Galileo, who had been the first person to see everything else in a telescope, at least by his ideas. So Galileo wrote a contrary book under the name of his student, Mario Guiducci. We've got the first draft. It's all in Galileo's handwriting. He says, look, let's just use it. Even though he never saw the comet, he says, I can use my reason. Comets are very rare. Even if it was the same comet coming back every 40 years, that would mean that they had an orbit even longer than Saturn's orbit, which would mean they'd have to have a distance even greater than Saturn from us. How could they be that bright? It's completely unreasonable. Certainly you couldn't have something like that in a circular orbit. Therefore, comets can't be in space. They must be refractions of light in the upper atmosphere. Grassi, using the name of one of his friends, writes a reply. This was the style of how people would debate. And after a while, each book is refuting all the things in the other book, whether it had anything to do with the argument of comets or not. So he writes a book called The Astronomical Balance. He says, let's put the evidence in two different pans. Comets show parallax, and besides Galileo, you don't understand how telescopes work. Because everybody knows, if you look at the moon, and then look at the moon through the telescope, the moon looks bigger, right? If you look at a star, and you look at a star through a telescope, the star doesn't look bigger. Therefore, the farther away something is, the weaker the magnification power. And therefore, since I couldn't see any difference in the brightness of the comet using the telescope or not using the telescope, it must be far away. And you don't understand that, Mr. Galileo, because you don't understand telescopes. This was the level of the discourse going on. Galileo, in his copy of the book, just writes, lousy buffalo. You can imagine what he thinks of. Finally, Galileo writes the reply, a book called The Assayer. Rather than using a rough kind of scales like you'd find at a butcher's shop, he's going to use the very fine scales that the assayer of jewels would use. And in this book, he outlines his philosophy of how science should be done. It's considered a classic. Kids in Italy today read this in high school just because it's such beautifully written Italian, clearly written for the popular audience. And in it, he argues that, first of all, I'm brilliant, you should listen to me. Secondly, the Pope, Urban VIII, is my buddy, you should listen to me. This is the same Pope who 10 years later is going to get him into trouble. Rely on the data that you have actually taken, not on what the ancients, because Grassi, being a priest, had been quoting all the ancient scholars in Latin. Galileo, being a college dropout, couldn't read Latin very well, so he said, don't bother with all these books written in Latin. Use what your own eyes have seen. And by the way, the comet, which I've never seen, can't possibly be, something out in the far sky. That's the frontispiece. That is a picture of a man who's phenomenally confident in himself and has a beard. Any resemblance between him and me is completely coincidental. Arrogant, nasty, smarter than everybody else in the room. Yeah, me. There's also, along with it, a poem in about 40 verses of how wonderful Galileo is, followed by the official church censor who writes that we are honored to be living in the same time as Galileo because we are going to be remembered for him. The church censor who endorsed the book was not a Jesuit, but a Dominican, the great rivals. And two more things about the outcome of this. First of all, what both Grassi and Galileo agreed on is that comets are not the portenders of great doom and catastrophe. And the fact that there were 3 comets in 1618 didn't mean that something horrible was going to happen in 1618. They both agreed with that. They were both scientists. 1618 was the year the 30 Years' War started. And secondly, Galileo managed to tick off so many of his enemies by being really clever and sarcastic that 10 years later, when the politics shifted because of the 30 Years' War, and he got into trouble, all the Jesuits said, yeah, gee, sorry to hear about that. But that's a different story. Comets still were mysterious, and were mysterious well into the early 19th century. This is a paper from the Philosophical Transactions of the Royal Society of London. We've got the complete collection going back to Volume 1, Number 1. Volume 7 has this little article by a fellow named Newton on a new kind of telescope he had designed, which he named for himself. In 1811, William Herschel is writing a paper trying to understand the structure and nature of the universe. And he says the key to understanding all of this is to understand how do we really picture nebulosity in the universe. And among the bits of nebulosity, and he lists about 25 different types of nebula that he's observed, are what he calls cometary nebulae, nebulae that have a cometic appearance. Among the numerous nebulae I have seen, there are many that have the appearance of a telescopic comet. A pretty large cometic nebula of considerable brightness. It is much brighter in the middle and very, very faint in the extreme, at the edges. Basically, he's looking at a globular cluster with a condensed core. And he's saying, this looks just like a comet. Maybe these are comets further out in our solar system who are going to eventually come and look at us. And maybe there's a whole population of these little things, because I can see them. Actually, we've got Messier numbers even. Remember, Messier had identified his objects because he was looking for things that weren't comets so that he wouldn't waste his time looking at them. Comets were fascinating through the 19th century, and there were a number of great comets that came through. and a number of people who finally had telescopes good enough that they could observe them. These are just two books in Germany that I found in our library, mostly because they've got lovely comets on the covers. And this is an illustration from a book of the Donati's Comet of 1858. Again, drawings by P.G. Bond. And it's also on the cover of this book. This was originally published in France in 1875. This is the 1877 English translation. Notice how thick that book is. For a topic about which nobody knew anything, he managed to put out a really thick... There's a joke among the Jesuits that there's the elderly Jesuit who had written the life of St. Joseph in 3 volumes. Those of you who know the life of St. Joseph appreciate. We have 1 sentence about his life, you know. Still, there was the next major breakthrough occurred around this time, actually in the 1860s, that really gave us our first clue as to what comets were all about. And it was associated with shooting stars. This is a photograph of a bunch of shooting stars of a shower. Comes from somebody who had worked at the Vatican Observatory, so let me use this. And as you can see, at time exposure, most of these are radiating out of a particular collection of stars. And if I impose HA ray on top of them, you realize that what they're radiating out of is the constellation Leo. These are known as the Leonids. There was an Italian astronomer named Schiaparelli who realized, and my idea of what is a brilliant astronomer, somebody who can do things that I couldn't, that this pattern comes from the Earth plowing through a string of dust just as it's approaching the direction of constellation Leo. And because he knew the periodicity of the great showers, which came once every 33 years, and from seeing where the Earth was when these all seemed to be coming out of Leo, he was able to calculate backwards the orbit that all of this dust should have and recognized that this dust shared exactly the same orbit as a comet. What he published was the connection of the Leonids with Comet Tempel-Tuttle. But when you look in his literature, he actually first worked it out for the Perseids of 1866. And of course, we're going to see the Perseids tonight. So now we know there's a connection between dust that makes meteors and comets. Schiaparelli was famous for 3 really major advances that we're all familiar with. He was the first person who discovered the canals on Mars that aren't there. He was the one whose very, very careful observations of the surface of Mercury showed that it always keeps the same face to the sun, which it doesn't. Both cases, the observations were really good. He just slightly overinterpreted. By recognizing that the connection existed between comet dust and comets themselves, Schiaparelli realized we must get comets from strings of dust who are gravitationally collapsing themselves into comets. It was only 10 years later that they realized one of the periodic comets, Comet Biela, had a dust stream attached to it called the Andromedes. You've never heard of the Andromedes. They don't exist anymore because the comet failed to appear in 1866, and there was nothing but a dust storm in 1872, and after that, the dust pretty much went away, which was the real observational evidence that the dust comes from the comets. The comets don't come from the dust. Nonetheless, this idea that there's a connection between dust streams and comets is in the literature up to as late as 1948. A paper by Littleton on the origin of comets. And this is his theory of where comets come from, 1948. During the passage of the sun through a cloud of interstellar dust, the particles are accreting onto the sun, and if they run into each other before they hit the sun, they're going to make a string of dust, and this string of dust will then gravitationally collapse into a whole string of comets. And the comets themselves will be what he calls sandbanks, collections of clouds of sand hold out whenever the sun passes through a cloud of interstellar dust. This same volume of the monthly notices of the Royal Astronomical Society has a number of other spectacular papers. A suggestion that the sun has a magnetic field because it spins, and all spinning things should have magnetic fields. Wrong. Not one, but two theories for the steady state universe that get rid of that stupid Big Bang theory, one by Tommy Gold and the other by Fred Hoyle, both wrong. And the idea that the Earth really doesn't have an iron core, but it has a phase transition from molecular to atomic phases. 1948 was not a great year for the monthly notices. But it was only 2 years later that two spectacular papers about comets finally came out. The first was by Fred Whipple. And Fred is interested in something completely different, something that had been noticed by Encke back in the 19th century. Comet Encke is a short period comet. It's only got a period of 3 years, but its period shrinks by a couple of days every orbit. And no one could understand why. It doesn't completely follow Kepler's laws. And Whipple said, here's why. Comets are made up of ice and dust, and when they get close to the sun, the ice evaporates, and it gives you a little jet off the side of the comet, which will nudge the comet out of its perfect Keplerian orbit. And he works the numbers, and the numbers work so well that it can explain both how come the comets are moving and also why you've got tails. He doesn't use the phrase in the paper, but everybody soon refers to this as the dirty snowball model. And essentially, that's what we understand comets to be today. In this paper, he also makes reference to a rather more obscure paper published the same year in Holland by a fellow named Jan Oort. Oort suggests that from a score of well-observed original orbits, that new long-period comets come from regions from about 50,000 to 150,000 AU distance. And that means the sun must be surrounded by a general cloud of comets of a radius about this order, containing hundreds of millions of comets. The total mass of the cloud is about 1/10 to 100th the mass of the Earth. And they're perturbed out of this cloud by passing stars or who knows what. The logic is perfect. Let's say that every year you see a new long-period comet. By observing very carefully the orbits of these comets, Oort was able to show that they were not parabolas like people had assumed, but actually just very, very, very eccentric ellipses with periods of millions of years. Well, if you've got a comet with a period of 10 million years, and you see one of these a year, there must be at least 10 million of them out there, right? In order to get one a year. If they're in really elliptical orbits, they're spending most of their time at aphelion, so they must be out there at, if it's got a period of 1 million years, it's a 10,000 AU. If it's, a couple of orders of magnitude more, it's going to be another order of magnitude. And because long-period comets approach the sun from every direction, not just the plane of the planets, not just the ecliptic, the cloud must be roughly spherical. It's impeccable logic. Nobody's been able to gainsay it. We still talk today about the Oort cloud. Even though we've actually still never been able to see it, how could we? The comets are so far away that even our best telescope couldn't possibly pick them up. But I want to emphasize what this was based on. This was based on the orbits of all the comets that Oort had been able to get good orbits for. How many comets are we talking about? Not many. 10. With another 5 that are pretty long period. Even today, we know of 500,000 asteroids with orbits good enough that we can actually predict their paths. 500,000 asteroids. We have observed less than 5,000 comets in the history of humankind, and less than 200 of them are periodic that we can actually predict when they're going to come back. Comets are still pretty rare and pretty poorly understood. But Oort, beyond saying that there's going to be a cloud of stuff, came up with a different version of where do comets come from, because he recognized if you're talking about something that far from the sun, there could not have been enough material in the cloud of gas and dust that made up our solar system at that distance to make these comets. The comets could not have been made there. They must have been made from someplace much closer to us. And that's basically what all this text is saying, to remind me to say that. How is it possible to get stuff made in the plane of the sun out to weird orbits? And the answer, of course, is Jupiter. We know that Jupiter's resonances kick stuff out of orbits and can perturb these orbits into wildly eccentric orbits. Now, in case anybody here is not familiar with a resonance, ask a little kid what it's like to be on a swing. If you're sitting on the swing and you rock your legs back and forth, and if you're a small child, you're able to exactly calculate the natural period of the pendulum that you are and rock your legs at precisely the period that you've calculated, because it's, the period goes as the square root of the length of the, well, you kind of know when you've got it, because when you've got it, you're pumping the swing, and the swing gets bigger and bigger and bigger and bigger until it goes over the top and you turn it inside out. Never done that, but I always wanted to. Resonances are when you add a small perturbation at the same time in the same place at some small fraction of its natural resonance. So if you are Jupiter orbiting once every 12 years, and there is an asteroid that orbits the sun once every 6 years, the asteroid and Jupiter are going to encounter themselves in the same part of each of their orbits every 12 years. Jupiter will give a little bit of a nudge to that orbit, and that nudge will build up over time so that the eccentricity of the asteroid gets bigger and bigger and bigger, so that even though it's still got the same period, it starts approaching other planets, and that other planet can give it a weird kick to finally get it up into the sun or out into the outer solar system. We know that even though there's lots of planets, there's a lot of stuff that went into Mercury and a lot of stuff that went into Venus and a lot of stuff that went into the Earth, bigger and bigger and bigger. Suddenly, Mars is a lot smaller than the Earth, and then you have the asteroid belt with hardly anything, because Jupiter ejected most of that stuff, clearing out the asteroid belt with boundaries of where things are cleared out that exactly match these small resonances with Jupiter. This has been known for 150 years. About 10 years ago, a bunch of guys in Nice came up with this Nice model. If Jupiter is moving inward, if Jupiter is kicking things outwards, then by conservation of angular momentum, it has to be moving inwards. If it moves inwards, then there's going to be a time when it's in resonance not only with the asteroids, but also with Saturn. And it's going to cause Saturn's orbit to become eccentric, and that's going to do other weird things. This is the first version. The models are now much more sophisticated. But here you've got all the dots of things that never got made into a planet because they're too far away from the sun to find each other. And then you've got colored orbits. The sun's at the center. The red orbit is Jupiter. And what's the planet after Jupiter? Saturn. So that's the yellow orbit. And then after Saturn comes Neptune. That's the blue orbit. And then after Neptune comes Uranus, and that's the purple orbit. There's a little kid in the audience who's going, it's the other way around. Watch me. Suddenly we hit resonance, and what happens? The outer two planets switch orbits, and everything gets scattered to heck. You want to see that again? All right. You know, we're missing the space station right now? Okay, well,
Oh, there it is.
I'm being overdone by the space station. I'll wait till it goes. Ooh, there it goes. The point is that we not only have a mechanism for throwing material out to the Oort cloud, but we also have a mechanism for clearing things out to beyond the orbit of Neptune. And of course, as Neptune moves out, maybe it picks up lots of other little scraps of material as it moves, which are in resonance with it. This is the current solar system. We've got the 4 outer planets there. All the blue dots are short period comets that we know are close and visible. And all the red dots are a region of material that was proposed ought to be in the plane of the same planets, but a source of a different kind of comet. Now, when Pluto was first found, Leonard, a meteoriticist, proposed perhaps it was the first of a population of objects out beyond Neptune. So it should be called the Leonard population. Well, no. 10 years later, Edgeworth comes up with a theory that maybe short period comets come from this population, so it should be called the Edgeworth. Actually, at the same time, Kuiper writes a book where he says, I don't really believe this theory. It's been called the Kuiper Belt ever since. But this is the picture. Now, mind this is a logarithmic kind of picture. You've got a cloud of comets around the solar system and a disk of comets closer to the solar system. And among the comets we see today, we can distinguish between long-period Oort cloud comets and Jupiter family comets, because these are the comets that are strongly perturbed by Jupiter because they're already in the same plane as Jupiter's orbit. The weird thing is, the Jupiter family comets probably come from the Oort cloud outside of Neptune and represent stuff from the outer solar system. The Oort cloud comets, which are actually way further out, originated much closer to Jupiter and were scattered out. So the guys that are close are really farther, and the guys that are farther come from closer. And the guys that are called the Jupiter family comets are the ones that were not scattered out to where they were by Jupiter. Have I confused you all yet? To understand comets, you would expect that there would be a chemical difference between short period and long period comets, and for a while it looked like there was. As we observe more and more comets, we realize it's less and less a good assumption, but there's still a hint of a difference in chemistry between Jupiter family and long period comets. But if you really want to know what a comet is like without that ugly tail getting in the way, you want to be able to observe comets where they live. And we know there's a whole population of comets living out beyond Neptune, the trans-Neptunian objects. And we started discovering these in about 1995. We have now found more than 1,000 of them. You can classify them by how they orbit. There's a bunch in blue, which are kind of just sitting out there in pretty much circular orbits, or not circular, but close to circular, in the plane of the solar system. There are some that have been scattered out of that. There are some that have been scattered in, which we call centaurs, because they're half comet, half asteroid. And then there are these guys we mark in red called Plutinos. Now, this is a diagram that I love because it kind of illustrates what's going on. But I'll step you through it because maybe this is the kind of thing that makes your eyes glaze over. Semi-major axis. This is the average distance. That's why I don't do that. Okay.
I got it. No, you're good.
Now I know
You're
not to
good.
do
You're
that.
good now.
Semi-major
You're good
axis. Semi-major. Oh, you can try it again.
There you go.
Okay. Semi-major axis. This is the average distance of the object from the sun. Perihelion is the closest that it comes. Obviously, nothing can be above a 45-degree line because the average distance can't be less than the closest distance. But if the average distance is exactly the same as the closest distance, the thing's going in a circle, right? The period that it takes is directly connected to the average distance. How farther it is, that tells you the period. Whether it's eccentric or not. So you see all these guys in red, they all have exactly the same average distance as Pluto does. They're all in a 3-to-2 resonance with Neptune. One picture is that as Neptune moved out, anything that suddenly found itself in a 3-to-2 resonance with Neptune's new period got trapped into that resonance and stayed in a 3-to-2 resonance, even as Neptune continued moving out, so just collected a bunch of guys. And that's kind of the argument as to why you really can't think of Pluto as a planet, because Neptune jerks Pluto around. Pluto doesn't have anything much to say about it. So Neptune's the planet, and sadly Pluto isn't. You'll notice there's a bunch that are right on a beautiful line among the blue guys. Those are the guys that we didn't have eccentricities for, so we just assumed they were circular. But you can see the 4 different populations there. The red guys are the Plutinos, the blue guys, which are the classical ones, the ones shooting off to the right there, which are the scattered disk, and then all the centaurs, which are the ones that have been scattered in to become eventually comets. And the people who do the numerical calculations say that things get scattered out of the one belt, they get junked down into really eccentric orbits, which then jerk them closer in, and eventually these guys become comets. If that's the case, if these are where comets come from, and it sure looks like they are where comets come from, at least the Jupiter family comets, we should be able to make some guesses as to what the surfaces ought to be made out of. Because we know things in the outer solar system are made out of ice. Now, it can be water ice, it can be methane ice. Methane, that's like natural gas. Ammonia ice. And if you irradiate this stuff with solar ultraviolet light, eventually you'll break up the carbons and they glue together and they make themselves little chains. And when the chains get long enough, you get colored material such as carotene. Yeah, comets should be about the color of carrots. A nice orangish red. But it also predicts that if that's the case, then you started out with this gray body, this kind of bright white icy body that got turned redder and redder and redder as the surface got exposed to the sun. And then maybe something hits it, splashes fresh stuff out onto the surface. If that's the case, then you ought to see a gradation in colors from red to gray, the red ones being dark, the gray ones being fresh, and any time you had a body with a fresh crater, it should be like gray or white on one side and red on the other side. So is this true? In order to find out, you've got to observe a lot of these guys and just work out the colors. You look at them in red, green, and blue filters and see, are they gray, are they blue, are they red? Tegler and Romanician, a couple of astronomers, one at northern Arizona and the other at Oklahoma, started doing this, and Fred Hoyle, my favorite crazy astronomer, noticed the results. That they have found that some of these are remarkably red. And of course, this means organic, and organic to Fred Hoyle means extraterrestrial microbiology. Well, not really. Tegler and Romanician were needing a telescope to make these observations, and we at the Vatican have a telescope. So they said, hey, can we use our telescope? So for the last 15 years, I've been observing with them on our telescope. Now, I hope you can indulge me, because I'm going to talk a little bit about telescopes. Anybody here interested in telescopes? Let me tell you about the telescope we built. We've got this telescope on Mount Graham in Arizona, which is a beautifully dark site in the middle of nowhere. Not only is it in the middle of nowhere, but there's no water there, so there's never going to be anything there. And it's on a mountaintop that's over 10,000 feet high. And it's a beautifully dark, beautifully dry site. How did it happen that the Vatican has a telescope there? Well, you've heard about the 200-inch, and you know what a pain it was to build the 200-inch, and you've made your 10 inches, and you know how much of a pain it is to build that. In the 1980s, a fellow at the University of Arizona had a new idea for making a telescope mirror. Take your glass and put it in an oven and spin the oven, the glass can flow over a bunch of forms so you have a honeycomb shape, but the shape of the glass is going to naturally move itself into a parabola. He got money to build a prototype oven, made a mirror, and then came to the Vatican and said, I'll give you the mirror if you build a telescope around it, and we'll share it 75-25, 75% the Vatican, 25% the University of Arizona. That's our mirror. That's Steve Tegler, Bill Romanishin again. And it was made by an angel. Because the guy who had the idea was named Roger Angel. 1.82 meter aperture. And because you can make the fastness or the slowness of the mirror just by changing the speed at which you're spinning it, they said, what the heck, why not? Let's give it a focal length of 1.82 meters. It has excellent images for a reason I'll explain. And the reason is that it has Gregorian optics. Now, as you know, a parabola is great at focusing things on axis, and not so good focusing things off axis, as anybody with a big daub and trying to look around the edges of a wide field of view will tell you. It's got coma. The way to correct for coma is to have a curvature, or one way, is to have curvature in the secondary mirror. For the typical telescope that doesn't have a really fast mirror, you bring in the light to hit the secondary before it comes to a focus, and then it comes to its focus as it goes through the hole down the bottom. But that means the secondary has to be convex. And measuring a convex mirror really precisely, I don't have to tell you guys about. By having a really fast mirror with an f1 aperture, f1 focus, you can have the focus go beyond the focal point, hit a concave mirror, which can be incredibly wonderfully carved and tested. The effective focal length by the time you get to the bottom is f9, which is what the instruments are used to. This only works if you've got a really fast mirror, because otherwise the telescope is ridiculously long. Nobody had ever made a Gregorian telescope of this size before. Nobody was sure if you could actually make it work, because if anybody's used a Gregorian, you know that it is really, really tricky to focus. Our telescope has to have the secondary mirror in a position to within 5 microns in order to have it in focus. It's all computer controlled, but it was all brand new. This is 20 years ago. Nobody had ever done such a thing. But being the Vatican, we weren't afraid to take a Gregorian chance. With this telescope, we were able, because the optics are so good, we are able to get sub-arc-second seeing without adaptive optics. Just point the telescope, focus it to within 5 microns, and the spot is better than the CCD chip. We can bin CCD chip pixels because it's just beautiful imaging. And that means you can look at something really faint because the light is concentrated into 1 or 2 pixels in your CCD chip, and you'll still get a good signal. Okay, remember our different categories of KBOs. The Plutinos, it turns out when you measure their colors, they're all over the place because these are guys that have been gathered from everywhere. The scattered disk objects seem to have a bunch of gray guys and a bunch of red guys, but a few things in between. But the actual cold classical guys are all red. And the centaurs that are being scattered in are either white or red with hardly anything in between. Exactly the opposite of what all our theories were about. Nobody completely understands why this is. We've been able to observe some of these objects with the infrared satellites and discovered if you know the infrared color and the visible color, you can work out how dark they are and how big they are. And the gray guys are as bright as the red guys. So there's no logic. And all of our predictions of what you ought to see turn out to not be true. We seem to be seeing a bunch of primordial objects that are either one color or the other color. We also thought that comets might be, collections of sandbanks originally, or at least collections of a lot of dust. But we know from Comet Shoemaker-Levy, when it passed by Jupiter and was ripped apart by the tides of Jupiter, it was not ripped into a zillion pieces, it was ripped into about 25 pieces. Each of those pieces was coherent enough and strong enough to hold itself together against tides. Do we see other examples? Well, Comet West that I told you about broke into 4 pieces. On April Fool's Day in 2006, we were trying to observe this Centaur, Echeclus, and discovered, turns out somebody else had seen it a couple of weeks before us, so we don't get the discovery, a cloud of light, not around it, but next to it. When you torque up the contrast, you see that actually there was a whole lot of light there. This was a lot of gas coming off of some piece orbiting next to Echeclus. And oh, by the way, you see that guy there? You see that guy there? That's what happens when a moth dies and lays its leg on top of the CCD chip. Naturally, the most important image we ever took has a moth leg on top of it. A number of other people, including people at Caltech and people using space telescopes, observed this over the next couple of months, and I just want to sort of give you an idea. This is a series of pictures of the same object, but you can see how the cloud of light moves around it with time. A few years later, people observing it was out by the orbit of Neptune at this point, about 13 AU. People observing it later didn't see it. About a year ago, it was reactivated again. Our best understanding, and this has not yet been published because the student who was going to publish it, who really found it the first time, went back to Korea and so far hasn't gotten around to writing it up yet because he's gotten other things to do. Our best guess is that what we have is Echeclus had an impact, broke into a couple of pieces. The other object is in an orbit that follows it around. They're close together in 2006, and they were close together 1,621 years ago, which may be when the 2 pieces broke off. One of them is active and the other isn't, and you can wave your hands about, well, maybe one was in the sun with some very low volatile ice, amorphous ice, that sort of thing. We don't know what's going on. One of the more wonderful but frustrating things about comets is that we finally have actually sent spacecraft to them. We can see the jets of stuff coming out not over the entire comet, but just certain regions of the comet. The first comet that, well, of course, we saw Comet Halley with the spacecraft in 1986, the Giotto spacecraft. The images were not very good because they didn't expect that the surface of the comet would in fact be jet black. In Deep Space One spacecraft, observed a comet close up and found these marvelous complicated terrains. There are these plateaus that appear to be flat, but with a cliff around them, like a mesa, and the jet seems to be coming out the side of the cliff and interfering with each other to turn into a jet that looks like it's coming straight out of the cliff, and people said, aha, now we understand what jets are. And we've looked at 5 other comets and never seen anything like this again. To get an idea of what this comet looks like, especially the people who are right in front of me, there are 2 images, right? Cross your eyes until you can just see one. And you should be able to see it in 3D. And you can see that the bottom piece is angled out towards you. and that if you keep doing this very much longer, you're going to get a headache. Comets are interesting in that clearly they're lumps of stuff, but they're not just piles of dust. We know what some of the dust from the comets are because we actually had a spacecraft go out and pick up dust. This is comet Wild. Looks completely different from the other comet. Instead of having mesas, it's got holes. What's going on? Well, cross your eyes on this one, and you get an idea of just how deep those holes are. Able to get it? And of course, we even have the dust from that comet. And the dust, in many cases, looks like the kind of high-temperature dust you find in meteorites, which, again, nobody explained. The problem is, if you had asked me to give this talk 15 years ago, I could have spoken with great authority about comets. But darn it, we have too much data now. We even threw something into the side of a comet, Tempel 1, which had took the picture of the other comet that I started this out. Sent an object to impact into Tempel 1. Splat! And that was the piece that went in, a large lump of copper. This is what it looked like from the outside. And by measuring the plume and looking for the shadow of the plume, you're actually able to work out how big was the crater that it made and what was the path of material. Again, you see sort of those mesas, but you see things that you didn't see in other comets. Circular objects, well, are they impact craters? Are they stuff coming out of the comet? No two comets look alike. The spacecraft that collected the dust from Wild 1 then was steered past Tempel 1 to take this image 5 years after the impact. And our best guess is that very, very fuzzy round thing is the impact made by the sphere that was sent in there. The thing that's cool, though, is by seeing how the plume behaved, you can guess how much gravity the comet has. And by knowing the size of the comet and the amount of gravity, then you know how much mass it is, then you know what its density is. And its density is about half the density of water. Now, what has, the density of rocks are around 2 to 3. The density of water is around 1. What's got a density of half that? The answer is nothing. Nothing mixed in with water and rock. These guys, unlike the asteroids that are, piles of sand are 50% nothing and then 50% sand, these comets are 80% nothing and 20% rock and ice. They are very fluffy, very low density collections of material where every one of them seems to be different from the previous one. And that's why they're so exciting, and that's why they're so hard to predict. Not just when they're going to come, which we still can't predict the long period, guys, but even what we're going to see. There were two great controversies in the 19th century of people who observed a comet, published their results, and then after the results were published, the other scientist says, "We don't believe you," but by then it's too late to go back and check again because the comet's gone. In both cases, people were accused of faking their data. And it's hard to convince people, no, I really saw what I saw, because no two comets are alike. The comet we're all excited about, Comet Ison, this is as imaged by Hubble a few months back in May. If it had continued to grow in brightness as much as when it was first discovered, then it would be a really bright comet. Well, it's not growing that bright. We don't know what's going to happen. We do know its orbit. We do know that with a really good telescope and you know where to look, you might possibly be able to naked eye it by now, but it's still pretty darn faint. Really, you start looking in early November, before the dawn. It hits perihelion about November 28th, And then it's going to be far enough to the north that you can see it just after sunset or just before sunrise in early December, if we're lucky. There are two things about being lucky that you have to worry about. Is it really going to be as bright as we hope? And is it going to survive perihelion? And I'm going to end with a little movie that people at Goddard put together about comets like ISON and ISON itself. And I hope the sound comes through.
All the comets that we can see from Earth are orbiting the Sun, but some belong to a special group called sun-grazing comets. Sun-grazers are comets that come very close to the Sun at their nearest approach, a point called perihelion. To be considered a sun-grazer, a comet needs to get within about 850,000 miles from the Sun at perihelion. Many come even closer, even to within a few thousand miles. Being so close to the Sun is very hard on comets for many reasons. They are subjected to a lot of solar radiation, which boils off their water or other volatiles. The physical push of the radiation in the solar wind also helps form the tails, and as they get closer to the Sun, the comets experience extremely strong tidal forces, or gravitational stress. In this hostile environment, many sun-grazers do not survive their trip around the Sun. They don't actually crash into the solar surface, but the Sun destroys them anyway. Many sun-grazing comets follow a similar orbit, called the Kreutz path, and collectively belong to a population known as the Kreutz group. In fact, close to 85% of the sun-grazers seen by the SOHO satellite are on this orbital highway. Scientists think one extremely large sun-grazing comet broke up hundreds or even thousands of years ago, and the current comets on the Kreutz path are the leftover fragments of it. As clumps of remnants make their way back around the Sun, we experience a sharp increase in sun-grazing comets, which appears to be going on now. Comet Lovejoy, which reached perihelion on December 15, 2011, is the best-known recent Kreutz group sun-grazer, and so far it is the only one that NASA's Solar Observing Fleet has seen survive its trip around the Sun. Comet ISON, an upcoming sun-grazer with perihelion on November 28, 2013, is not on the Kreutz path. In fact, ISON's orbit suggests that it may gain enough momentum to escape the solar system entirely and never return. Before it does so, it will pass within about 40 million miles from Earth on December 26th, assuming it survives its trip around the Sun. All comets are great laboratories for scientists to learn more about our solar system, but sun-grazing comets can also help us learn about the Sun. Their tails of ionized gas illuminate invisible magnetic fields, so they can act as a tracer, helping scientists observe these normally unseeable features. Such fields have even ripped off comet tails, allowing astronomers to watch them blowing in the solar wind, a wind that abruptly accelerates between 1 and 5 million miles from the Sun. Because of this, researchers will be watching ISON and other sun-grazing comets very closely. And since we are in a period of high sun-grazing comet activity, scientists can expect many more chances to watch these beautiful, natural research satellites in the coming years.
So thank you, Goddard, and thank you for everybody here. It's a glorious night, and I don't want to hold you any longer to do some fabulous observing.